Hello, this video is to show you how to formulate a linear programming model. In one of the tables, we will have two variables, and the second table we'll work with is two or more variables. So in the first one with two variables, we have a word problem that says a window or glass company produces high quality glass products, including windows and glass doors. It has three plants. Aluminum frames and hardware are made in plant 1, wood frames are made in plant 2, and plant 3 produces the glass and assembles the products. Because of declining earnings, top management has decided to revamp the company's product line. Unprofitable products are being discontinued, releasing production capacity to launch two new products having large sales potential. So product 1 is an 8-foot glass door with aluminum framing, and product 2 is a 4 by 6 foot double hung wood framed windows. So now looking at the table that we have right here, we have the plants 1, 2, and 3 that was mentioned in the word problem. We have is the products and products of 1 and 2 that is mentioned over here. So because this question is about two variables, we need to come up with decision variables of x1 and x2 and decide where our x1 and x2 is. Looking at this, x1 is going to be our product 1 and x2 will be our product 2. So if we know those two will be our decision variables, let's come up with a constraint and restrictions. So in our first equation, in plant 1, we have is 1 x1 is less than or equal to 4. And it's 1 because this right here is a number 1. It's a coefficient for our x1 right here. And because this right here is not an x2, it's going to be our restriction, which is then it's going to be less than or equal to 4. So plant 2 has 2x2 is less than or equal to 12. And again, the same idea. This right here is a 2 coefficient for the x2. There's a 0 in x1, so you do not include that in this equation right here. And the 12 is going to be our restriction right here. And so our third plant would then have is 3x1 plus 2x2 is less than or equal to 18 because each of these coefficients are being used. To come up with our objective function, we're using the last part of this table, which is the 3,000 and the 5,000. And it says right there, profit per batch right there. So this will help us to determine what is our maximum profit and our minimum profit as well. So in this problem, you can have two things. You can have z equals 3x subscript 1 plus 5x subscript 2. But then in your somewhere in there, make sure you put down that the dollars are in thousands, so you will know at the end your calculations will be a smaller number. If this confuses you where you have this small number right here, you can always write down all of these numbers right here. So you can write down as 3,000 x subscript 1 plus 5,000 x subscript 2, which then you won't have to worry about the at the end calculations because it will give you a true number at the end. Okay, so this is two variables. So now let's go into the next one, which is two or more variables. The Norian Leeds Company, one of the major producers of steel in its parts of the world, is located in the city of Steeltown and is the only large employer there. Steeltown has grown and prospered along with the company, which now employs nearly 50,000 residents. Therefore, the attitude of the townspeople always has been, what's good for Norian Leeds is good for the town. However, this attitude is now changing. Uncontrolled air pollution from the company's furnace is ruining the appearance of the city and endangering the health of the residents. A recent stockholders' revolt resulted in the election of a new inline board of directors for the company. These directors are determined to follow socially responsible policies, and they have been discussing with Steeltown, city officials, and citizens groups what to do about the air pollution problem. Together, they have worked out stringent air quality standards for the Steeltown airshed. We now have three different types of tables. Our goal is to find the minimizing objective, which is also known as the objective function, and also the subject to the restrictions, which is also known as the constraint or the restriction equations. So looking at the three different types of the tables, we want to find out is where the decision variable is going to happen. So remember, the decision variables are your x1, x2. Now in this case, you may have more than x1 and x2. Consider this table right here and say the particles are x1, the sulfur oxides are x2, and then the hydrocarbons are x3. We're going to have a problem because when we get to table 2 right here, we have a lot more things involved in here. We want to find the table that has more items so we can then decide what will become our decision variables. So let's look at the second table and decide that the first part, the blast furnace, will be our X1, the open hearth furnace will be X2. Notice that each of the three columns are different. This is the taller smokestacks, this is the filters, and then this is the better fuels. Underneath each of these three different items we have is the blast furnace, which is alike for all three of them, and then the open hearth, which is also alike for all of them over there as well. So if we say this is x1, x2, x3, x4, x5, and x6, now I can come up with three equations similar to the previous one when we did plant 1, plant 2, plant 3. So we'll come up with three equations. One is going to be the particles. And notice in the particles, I used the decision variables of our x1, x2, etc. The numbers in front of it are coming from here. Each of these numbers right here, the coefficients, that 12 coefficient for the x1, the 9 for the coefficient of x2, 25 for x3, 20 for x4, 17 for x5, and then 13 for x6. So doing the same thing, we're going to come up with two other equations. So for the sulfur equation, and then also for the hydrocarbons. Now from here, we only have the constraint equation. We don't have the restrictions. We need the restrictions, which is at the end of the equation we have is greater than or less than a number. So looking at this, we have particles, the sulfur and the hydrocarbons. We need a value of sulfur and we need a value for the hydrocarbons. So if I go into my next table up here, that's going to give us the same items. And so from there, I can use then the particles, which is equal to 60 right here for this particle right here. Okay, so then the equation will look something like this, where I have my greater than or equal to 60. And I'm using greater than or equal to 60 because it's asking for the minimizing. So if it's asking for maximizing, we're going to actually change our inequality to the other way, which is going to be less than or equal to. So that's going to be a difference, so make a note of that. If it's asking for minimizing, then it's always going to be this equation. All of this right here is going to be greater, or you can think of it as the number is less than, right? The 60 is less than all of these guys right here. Next equation are going to be the sulfur and the hydrocarbons. So same idea, we took the numbers for the 150 and then 125. So that finishes our constraints and restrictions as far as the equation goes. So now we have to find the next one, which is the minimizing objective. So this is going to be our objective function that we mentioned in the previous video. So since I have x1, x2, x3, x4, x5, x6 as my decision variables, again, I need to match that for my final equation. So the only table we haven't used is this last table right here. And this last table, we can use this to represent our coefficient for this. So if I use, for example, the 8 right here, which is the blast furnace, and again, the blast furnace right here, that's going to be our x1. Then for the open hearth, for the taller smokestack, it's going to be 10, which matches this right here, the open hearth for the taller smokestack. So that's going to be 10 right there for x2. Same thing for this one, 7 is going to represent x3, which is the blast furnace for filter. So same thing, filter, blast furnace, that matches. And then the last one I have is the filters for open hearth is 6. And so filter for open hearth right here, that's going to be my X4 right here, so that matches. And then our better fuels is going to be this right here, furnace, blast furnace for X5. So that's going to give us the 11, and then our urban hearth for x6, that's going to be our 9 right there. So that's how we're coming up with this part right here, and equals to z. And again, we use this equation once we look for each of those x decision variables for x1, 2, 3, 4, 5, and 6. We can put it into this equation to figure out what is our maximum and what is our minimum. So this is a video to convert our tables to decide what our decision variables are. From there, making our constraint and restriction equations, and then finding the objective functions.